Hello, Chris McKay here. You should be able to see my slides. What I'm going to talk about is good. I'm going to talk about what I call the prerequisites to human activity on Mars. I've got my email there and the date. And here's what I mean by Mars. We think about, when we talk about Mars, the case for Mars, we can parse it into four steps. First step, short-term missions involving a few astronauts. Second step, long-term research outposts, tens, maybe hundreds of people, similar to research outposts in the Antarctic. Antarctic research bases are a good model. Next step would be large settlements with populations in the thousands or even more. And finally, a vision of terraforming Mars to make it easily habitable for humans. So that's what I call the story, the Mars story. What I want to address here is the question, are there fundamental uncertainties in our ability to really implement these steps? Obviously, there's engineering challenges and projects and funding and things like that, but those are solvable issues. They may be difficult, but they're solvable. I want to talk about fundamental issues that may be much more difficult. The first one is the question of, is there life on Mars? The second one, is Martian life a second genesis? The third fundamental question is, how will life adapt to 1/3 gravity? And then the fourth fundamental question is there enough nitrogen, CO2, and water on Mars for terraforming? Each of these questions comes up in one step: humans, bases, cities, planets. And I'll go through each of them one by one and discuss the points. Here is the first question: is there life on Mars? Now we're imagining, and as you see in this picture, sending humans to the surface of Mars in the equatorial areas. The general view is that the low latitude surface of Mars does not have life. It is lifeless. That's the scientific interpretation of the Viking results. But the evidence is scant. There's only been one mission really that's focused on life detection. And the evidence in hand probably does not constitute due diligence with respect to returning Martian materials to Earth, e.g. the astronauts coming back, dust on their suits, dust in their lungs, dust on their hair. We are required by the Outer Space Treaty to be very careful in returning materials to the Earth for obvious reasons. So I think what this means is that we have to do a better job purely for this requirement, if for no other reason, to confirm that the surface of Mars has no life. So what we need, I think, is an in situ no life detection mission in advance of humans, so that we can check the box that, to the best of our ability to determine, the equatorial regions of Mars where humans would go and return from meets the Outer Space Treaty requirements for not contaminating the Earth. No life. So we need a no life detection mission. The next question, if there is life, is it a second genesis? And I bet this question will not come up until humans are on Mars, because if there's life on Mars, it seems to be in very restricted locations deep below the surface that will probably only be discovered by human exploration and deep drilling. And in fact, this is one of the main motivations scientifically for human exploration, is that humans and the infrastructure they have can do this sort of extensive exploration. So if we go to Mars, the surface is lifeless, but the deep surface has life. And if that life represents a second genesis, then this has implications for human presence. And I think the solution here is we must do our exploration in a way that's biologically reversible to keep the options open for what we decide to do if we find life that is a second genesis. The next fundamental question is, can life adapt to 1/3 gravity? Near-term missions, even the Antarctic-like bases, may involve humans going back and forth to Mars. They probably do not involve families with little kids and pregnancies. Antarctic bases aren't known for that. But if we're talking about cities on Mars, we have to think about what that's like. And how will life, reproduction, growth, early development, and 1/3 gravity be? Essentially, we're assuming that life will adapt well. As we conceive of cities on Mars, we're assuming life will adapt well to 1/3 gravity. But there is no data to support this assumption. And I say no data, I mean zero data. We haven't even done simulations in Earth orbit at 1/3 G with anything farther up the phylogenetic tree than a plant. So we have no data on how humans will adapt, how pregnancy will be carried to term, how infants will be born, how children will develop at 1/3 G. Now, if long-term growth and reproduction in Martian gravity is determined to be detrimental, this has important implications for the long-term human presence. We can certainly still go there, short visits, and maybe even large permanent research bases. But the idea of large cities with thousands and more people becomes harder to imagine. Finally, in the fourth phase, terraforming, the key question, surprisingly, is not can we do it, because we clearly can if the materials are there. We have learned to our surprise that we humans can warm up planets. And when I mean surprise, here on Earth, we've been surprised. And we could do the same thing on Mars. On human timescales, we could warm Mars with super greenhouse gases. But it's pointless to warm Mars if there's not enough material on Mars to make a biosphere. And that material is nitrates, CO2, and ice. How much nitrate is on Mars? We don't really know. We know it's there, but we don't know how much is there. How much CO2 is present as ice, carbonate, or minerals? We don't know. People have written papers suggesting it's this or that, but we won't know until we do deep drilling and do geophysical surveys. The question of volatiles on Mars is fundamental. If there's not enough of this material, then terraforming becomes science fiction. It moves to Star Trek-like technology and epics, and that may be still interesting, but it's not part of a near-term plan. So I want to go quickly to questions. So on the way to Mars, as I've said, and people have pointed out, there are many practical difficulties with human activities on Mars. You've got to develop biological life support systems, power systems, spacesuits, artificial gravity, dust control. These are hard problems, very hard problems. Some of them we don't even see clearly how to solve, but they're all solvable in principle. With effort and focus, we can solve them. And they are solvable here on Earth. We can solve them before we go to Mars. But the questions I've raised, the questions of life, second genesis, adaptation to 1/3 gravity, and inventories of nitrogen, CO2, and water are fundamental. They're actually not questions or problems to be solved. They are issues that can only be answered. The answers to these issues can only be discovered on Mars. Mars will tell us if there's life, if it's a second genesis, if we can adapt to 1/3 gravity, and if there's enough nitrogen, CO2, and water. We have to discover the answers to these questions on Mars. It cannot be answered on Earth. And unfavorable answers to these questions could derail the Mars story. Now, what's the point of this is that we ought to focus on some of these questions in terms of the robotic missions that go before humans and the initial science and field activities that humans do when they are on Mars. And as a good academic, of course, I write all this in papers and publish them in peer-reviewed journals. You know, that's what scientists do. So here, for your entertainment, is a list of lots of papers which go over these thoughts in detail, much more detail, obviously, than I can cover in a half-hour talk. And I'll happily send reprints, PDFs of these to anyone who wishes to have them. And this is the last slide. And Jim, I'm going to disconnect my sharing and open up for questions.
Hi, Chris, this is Lucinda. We're going to have Nora Hovey help us with the Q&A. So
Okay.
Nora, whenever you're ready.
All right. This is from Jerry Stone. What is the view of Gil Levin's experiments on the Viking landers? The positive results were overruled as the mass spectrometer found no carbon, but that was later shown to be faulty. So is it possible that we did find evidence of life on Mars back in the summer of 1976?
That's a very good question. And it's one of the reasons why I contend that the question of life is not closed. Although most scientists, most Mars scientists do not agree with Gil that he detected life, I don't think we can rule it out to the level of certainty that would be required to bring a sample back to Earth. So there's one level of certainty, which is the consensus in the scientific community. Okay, the consensus in the scientific community is Viking did not find life. What Gil detected was chemical reactivity. But is that level of certainty adequate to risk Earth's biosphere in returning a sample from Mars? I think clearly the answer is no. It would not stand up in court against a challenge that we had not achieved due diligence with respect to our obligations in the Outer Space Treaty. So this is an important point. The question of life is not locked down well enough to allow a human return. We need to do a no life detection mission. And hey, Gil might have been right. And this mission we send to Mars to confirm there's no life there might surprise us all, and Gil would be having the last laugh. I actually hope that's the case. I would love there to be life on Mars. But the expectation is it wouldn't be there, and what we have to do is document that well enough that we meet the standard of proof for the Outer Space Treaty and our legal requirements to protect the Earth.
Next question. Can you comment on any projects in the works that would scan for deeper water so we might know where to drill?
Yeah, that's a good question. When you say scan, then you could imagine radar. And in fact, there was a paper in Nature Scientific Journal just a couple weeks ago reporting on radar evidence for deep lakes in the polar regions of Mars. So indeed, we can scan the subsurface with radar, and we can look for subsurface lakes. And to everyone's surprise, we seem to have found some below the ice in the polar regions. Maybe we'll find some below ground in the equatorial regions. But we don't really get very good information from just these radar. We're really going to need to drill. The way we find out what's underground is to drill. So I would rephrase your question, if I could, as scan and drill for subsurface water or other resources. And drilling is very hard to do. With the robots, Curiosity got a few centimeters. ExoMars in a few years will get 2 meters. That just doesn't do it. We need to be able to drill a kilometer. And for that, humans are particularly well equipped. The best way to drill a kilometer is send a drill rig with a bunch of roughnecks, and they'll drill down a kilometer. So I've always contended that drilling deep below the subsurface is one of the most important scientific tasks that humans can do when they get to Mars. So if you want to be on the first crew, learn how to drill.
Next question. Can you explain the second Genesis theory?
Thank you for that question. It gives me a chance to go into one of my favorite topics in more detail. The interesting thing about life on other worlds is not just that there's life there, but that life might be fundamentally different from life on Earth. It might represent a second origin of life, what I call a second Genesis. Now, for many years, it was just assumed that if there was life on Mars, it would be a second Genesis. Aliens were from other planets. And if you were from another planet, you were an alien. But now we know that Earth and Mars exchange material via meteorites. And it could be that life started on Mars and was carried to Earth in meteorites, or vice versa. So we might well go to Mars, find life, and find that it maps on our tree of life. Google tree of life to see what I mean. And if that's the case, then life on Mars and life on Earth are related. There are cousins. Well, we might as well just move right in. Hi, cousins, here we are. If we go to Mars and find that there's life there and it is fundamentally different than life on Earth and represents the second genesis, that's amazing, because it would tell us right away that n equals 2. N being the number of life forms in the universe. It's at least 2. Right now, we only know that it's 1. If we find a second genesis on Mars, it would tell us that n is greater than or equal to 2. And by the by the 0, 1 infinity rule, 2 doesn't make any sense. You go from 1 to infinity, really. So it would tell us the universe is just full of life. Wonderful. But it would also pose the fundamental ethical and technical issue of, if there's life on Mars already, how do we establish life there, or do we establish life there? So it becomes much more problematic in terms of the story that I talked about at the beginning, if we find a second genesis of life on Mars. It's also, but it's much more scientifically and philosophically interesting, but it poses very important ethical and practical problems of contamination and infection and who knows what. You know, a good cautionary tale in this regard is rabbits in Australia.
Next question. This one is gives you an opportunity to dream a little. Once a permanent human presence has been established on Mars, what's the next step?
Well, I see 4 steps again. Small missions with a few astronauts, permanent long-term research bases, large cities, and then terraforming Mars. So those are the steps. Beyond that, okay, we've done that. Let's say we've gone to Mars. Everything's been fine. All of our questions have been resolved positively. We have cities on Mars. It's terraformed. Where do we go next? I think that's a really interesting question. I have no answer to it. There's nowhere else in our solar system that's anywhere near as good. The nearest stars are very, very far. I am afraid we might just end up sitting on our thumbs on 2 planets for a while.
Robert, do you have a question?
Okay, I have a question for Chris. Why do you imagine that the Outer Space Treaty is a problem that we cannot solve?
Well, the Outer Space Treaty, the US signed the Outer Space Treaty, and one provision of it is that we have to, quote, prevent the harmful contamination of the Earth. Now, we are bound legally, unless we step aside from the treaty, but logically, I think we have to have a very high precautionary approach to bringing back material from Earth that might have life in it. That is encoded in the Outer Space Treaty, but it's also part of the mandate of agencies like the Department of Agriculture. You want to bring something into the United States from the moon or from space, it's got to be cleared by the Department of Agriculture. And they care about, you know, is this a possible contaminant? So, yeah. And well, common sense tells us that we don't want to bring back life from another world without understanding it.
Okay. Well, those are arguable propositions, but they do not fall into the same category as humans cannot adapt to 1/3 gravity. Treaties, there are innumerable treaties that have existed in the past that have been abandoned or modified.
That could be the case. I'm not sure that I would advocate that we abandon the approach of not bringing back, or carefully, being very careful, extremely careful, and bringing back samples to Earth from anywhere that might contain alien life. That would, right now, that list on my part would include Mars, and it would include Enceladus. Sample return from Mars or Enceladus should be, even if you abandon the space treaty, should be, by common sense, treated with extreme carefulness and caution. And so astronauts coming back, it'll be very difficult to contain dust and Martian material if they're coming back, if astronauts are coming back. So you really, it's much more efficient to get that question out of the way before astronauts come back. If you look at the way they did it on Apollo, they tried to do the containment and control with the astronauts mission, and it really didn't make any sense. It was a farce. Well, fine, the moon, no one really had any serious concerns about life on the moon. But on Mars, I think the level of concern is going to be more severe. And so just from an engineering efficiency point of view, if you can check that box and discard it before you bring the astronauts back, you can dispense with any sort of control or issue of, are the astronauts bringing back dirt? Do we have to quarantine the whole capsule? Da, 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 da. And you could do that with a, quote, no life detection mission. Those missions are, I think, on the outside, even if NASA launches it, maybe $500 million. That will be probably a fraction of the cost of dealing with quarantine on the astronauts if you don't do that in advance.
Well, you can never prove a negative. So a mission that goes to one place and doesn't detect life would not prove that there's no life on Mars.
Correct.
And if
Correct.
there is life on Mars, there's very little reason to believe that it would be pathogenic to Earth. But nevertheless, while we can debate that, and we have debated it, and certainly the scientific community does not believe that it should not do a Mars sample return until it is proven that there's no life on Mars. I find myself in an unusual position of arguing the orthodoxy. But nevertheless, the fact is that while one can debate whether one should or should not do this or that, it is not beyond human power to deal with that situation. If Mars was a lush planet filled with life, that would not rule out going there unless we choose to rule out going there. It is not in the same category as there is not enough material on Mars to terraform the planet. Treaties can be changed by people deciding to change treaties.
Well, this is not really about a treaty. This is about risking the Earth's biosphere. Would we bring back a sample? Now, you say that the science community thinks that they'll bring back a sample without worrying about that. I'm not sure that's correct, and that hasn't been approved, by the way.
Well,
So,
no, the science community, though, is saying that it's willing to bring back a sample before it proves that there's no life on Mars.
But
okay, because actually you can't prove that there's no life on
no,
Mars.
we're not. If you noticed, I'm not saying we have to prove that there's no life on Mars. What I'm saying is that you would land where in the zone of Mars, surface, equatorial latitude, where the humans would go, and you would confirm to some reasonable level, due diligence is what it's called legally, that there's no life in that material, so that the astronauts would not be, the dust that the astronauts would be tracking on their spacesuits would have been shown not to contain any evidence of life at some reasonable standard. You are correct in that this does not prove that there's no life anywhere on Mars. And that leads to the second issue of the psychogenesis. You may decide that there's no life on Mars for the purposes of astronauts landing in the equatorial regions and coming back to Earth, and you may satisfy that requirement from terms of safety of the astronauts and the Earth's biosphere. And yet, when a human base is there, an extensive exploration, they may still discover life. Right? As you say, it is very hard to prove a negative, but you can prove it locally. And I think you're going to want to do that for a lot of reasons, some of which have to do with just science planning and bringing the astronauts back and avoiding the kind of debacle that they had with Apollo and quarantine the astronauts when they come back and all the costs associated with that. I think you'll want to have removed that issue completely from the discussion and the mission planning, and you can do it in advance with robotic missions. So you're in a position to be able to say, hey, I know that the area that they're landing on is good enough in terms of absence of life that these astronauts don't need to filter the dust to extreme levels to prevent contamination. They don't need to worry about getting sick. They don't need to worry about bringing dust home. We can relax all these constraints that might get imposed, and it can be done with a mission advance. You're right, it is not in the same category as these other constraints, but I didn't claim that it was. I'm just saying these are fundamental questions that we have to address. And if we don't address them, we risk derailing the story of Mars exploration that we would like to see implemented. By certainly, in no means are these the same. You can't say that adaptation to 1/3 gravity is the same category as volatiles on Mars or life in a second Genesis. I didn't mean to imply that. These are 4 fundamental problems, fundamental questions, the answers of which we will only find on Mars. That's my point. No amount of engineering on Earth will give us the answers to those questions. We got to go to Mars to get the answers.
Okay, I'll let other people ask questions.
Next question. What is the status of the 1996 Mars rock?
The rock in 1996, a meteorite called ALH 84001 was suggested to contain evidence of life on Mars. Since then, that meteorite has been the source of much investigation and much discussion. The conclusion is that it does not contain evidence of life on Mars. It does contain evidence of an early period in Mars history when it was more habitable, more Earth-like. So it's an interesting meteorite. Mars, it points us to an interesting phase of Mars's early history, but it doesn't really answer the question of life.
Last question. Can you comment on the long-term effects of the Martian environment, specifically the fact that the Martian day is 39 minutes longer and 1/3 the lower gravity? What effects will this have on humans long-term?
Yeah. Well, the 39 extra minutes, I don't think will be a big deal. I could use them today, actually, extra 39 minutes. I don't think that's a major issue. The 1/3 gravity, we have no idea. Not just me, but none of us have any idea what the effect of 1/3 gravity will be. We assume that we'll adapt fine and we'll just be just like living in 1 gravity. And maybe that'll be the case. The one sign of hope is that plants grown in space station at 1/3 gravity seem to have much better response to gravity than they do when they're grown in microgravity. So just looking at very limited data from space station and only at plants, one would argue that the threshold for gravity response occurs above 0, but below 1/3, and that 1/3 and 1 is about the same for plants. Now, whether it'll be the same for humans or not, we don't know, but we are hoping it will be, and we are assuming it will be, but the only way we'll find out is by going there.
Thank you very much, Dr. McKay. Thank you for being with us.